I would like to revisit the model of gravity that we developed in 121 and then talk about some ways that we can improve it. Okay, so recall that in 121, the force of gravity was just equal to the mass of an object times g, where g was 9.8 meters per second squared. Well, we had, in addition to the magnitude of the force, a potential energy function. So UG, the gravitational potential energy, was equal to mgy. Okay, and that was related just to the force because we could take that force times the displacement, and that was equal to the work. Okay, but we can ask, do these equations actually make sense? So they work okay if we're considering objects that are near the surface of the Earth. You know, if I have an object that's several kilograms and I lift it up, I know what force I need to exert on that object because I can figure out how strong the force of gravity is. But what if we considered what happens if you lift that object very far from the Earth? What if you lift the space shuttle, for instance, thousands of kilometers away from the Earth? Well, we might reasonably expect that equation would not work in other circumstances. What, for instance, would happen if we brought an object to Mars? Would we expect the same force of gravity on the object by the Earth if we brought the object to Mars? Well, no. We expect Earth to have almost no influence on that object, and Mars will then exert some different force on that object. And again, what if we were in deep space? If we brought the object very far from any stars or planets, would there still be a gravitational force on it? Is the Earth still exerting a gravitational force? Are other objects as well? And this equation is not suitable for that, because according to this equation, the Earth would be exerting a force of the same magnitude on that object no matter where in the universe it is. And that doesn't really make a lot of sense. It is our experience that things that are very far away from us tend to have almost no effect. So, for instance, the Andromeda galaxy is very large, but it is not having a significant gravitational effect on us in our everyday lives because it's very far away, and so we ignore it completely. Okay, so if the equations we have for forces and energy in gravity don't really make sense for cases like the ones I just talked about, then how can they be improved? Well, I'm going to introduce now a new law, which is Newton's law of universal gravitation. Okay, or as I like to abbreviate it, NLUG, because that's a lot of words. Sometimes people will call this by slightly different names, so it might be called just the law of universal gravitation, or Newton's law of gravitation, or some other combination, but it's always referring to the same law. And the history behind this, and it's not really clear how much of the story is true, is that Isaac Newton was considering what it was that was causing the moon to stay in orbit around the Earth. Back in that time, the motion of astronomical objects was considered completely separate from any phenomena that we were familiar with near the Earth. So while Isaac Newton was out in an orchard thinking about this, he happened to see an apple fall. And he had the brilliant insight that perhaps the force that's keeping the moon in orbit around the Earth is the same force that is causing objects near the Earth to fall. There's this attraction between the Earth and the moon, and it's no different than the attraction between the Earth and the apple. Okay, so that was wild insight that was totally different than the way anyone had been thinking about these things before. So, based on some information that was available to him at the time, he came up with the following law. So, Newton's law of universal gravitation says that the force on one object by another object is equal to some constant g times the mass of one object times the mass of the other object divided by the distance between them squared. Okay, so that is the magnitude of the force. So we can just plug in those numbers and get a magnitude for the force. But there's got to be a direction as well. So if I make this into a vector like so, then the direction is toward each other. So gravitational forces are attractive forces. They attract two objects to each other. Okay, so g is just some constant. And we'll talk a little bit later about how we would get this. So its value is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay, and you can check that if you plug in g and some reasonable values for the other quantities, then you will in fact get a force in newtons. Okay, so this is an equation that works. Let's see whether it makes sense in any reasonable cases. All right, so first of all, if I plug in, let's say, a 1 kilogram object that's attracted to another 1 kilogram object, and they're, say, a meter apart, what size of force do I expect? Okay, well, I just try it. So I'll have two 1 kilogram objects 1 meter apart. So if I plug that in, then I'll get g times 1 divided by 1 squared. And so at the end of the day, what I get is that the force in this case is equal to 6.67 times 10 to the negative 11 newtons. Okay, the kilograms in g cancel with the kilograms of the masses. The meters in g cancel with the meters in the distance. Okay, so for two ordinary sized objects that are an ordinary distance apart, we get this monumentally tiny force, which is why we never notice it. In our everyday lives, objects are attracted to each other with gravitational forces, but it's so much smaller than any other forces that are present that we never ever notice it. Interestingly, it is possible to detect that, and so people do experiments every day where they are able to detect forces of that magnitude between everyday objects. So if you're skeptical about this being really true, I can assure you that there are plenty of experiments that detect those kinds of forces directly. Okay, so what else is true about this Newton's law of universal gravitation? Well, notice that if I consider the force on object 1 by object 2, or I consider the force on object 2 by object 1, I always get the same size of force. Well, that's good. I need to have that property because of Newton's third law. So the two objects have to be exerting a force on each other of the same magnitude and in opposite directions, because from 1 towards 2 or from 2 towards 1 are going to be opposite directions. Okay, so Newton's third law is satisfied. Okay, so sometimes it's helpful to write this equation in a more vector conscious form. So this will give you the magnitude, and you can try using, whatever tools are available to you to try to figure out the direction. But we can actually do this a little more carefully and make the direction work out automatically. Okay, so what I'm going to do to have that happen is I'm going to say the force on object 1 by, instead of calling it object 2, I'm going to say by the source. So I'm going to imagine that there's some object that is the source of the gravitational interaction, and the other object is experiencing a force because of it. Okay. So I haven't really changed anything. I'm just naming object 2 the source. Okay, and that's going to be equal to g times m1 times m source over the distance between them. And this time I want to treat this as a displacement. So I'm going to write this as though it's a vector. So the order I write these in matters. So I'm going to call this the R, which is going to be the position of object 1 from the source. Okay, so instead of just calling it R12 or R1s, I'm going to be specific about which way the vector goes. It's going from the source to 1. Okay, and again, that's going to be squared in order to be consistent with Newton's law of universal gravitation. And then the direction will be R of 1 relative to the source hat. Okay, where a hat, remember, R1s hat equals R1s vector over the magnitude of R1s. Okay, so R1s hat is a dimensionless vector. It just gives us a direction. It has a length of 1, and so this gives us the direction. Okay, so to kind of clean this up a little bit, I've written all of the details in terms of the subscripts, but I could write this a little more cleanly. So F1s equals G M1 MS over R1s squared R1s hat. Or, if you don't like having the hat in there, well, we can use the way the hat is defined, actually, in order to write this as G M1 MS over R1s cubed R1s vector. So all I did was take the hat and replace it with R1s vector over R1s magnitude, and so now I don't have any hats. So whichever way you prefer is perfectly fine. So this is a way that we can write out the gravitational force in a completely vector form. So if you were going to, for instance, write a simulation, then this would be nice, because if you know all the positions, then you can just plug everything in and you don't have to figure out the directions. For most practical purposes, if you're trying to solve a problem that has some modest number of forces in real life, you don't really need to worry that much about the vectors. You can just figure out the magnitude and then by hand figure out which direction it's in. That's the way I would approach it in most cases, unless you really need to be careful about finding all of the components, or you were doing it systematically by computer, for example. Okay, so there's one more detail that I forgot here. So if we're calculating the force that is on object 1 by the source, and we define R to be from the source to 1, then the force is actually from 1 towards the source, because they're attracted towards each other. So in order to make this work out right, we need a minus sign here in each of the terms. Okay, and again, that's just a detail to get the direction correct. If you forgot the minus sign, then it would point away, and that would be, I think, obvious right away. And if you defined R to be, instead of from the source to 1, you could choose to define it to be from 1 to the source, then you would not have a minus sign. So really it just depends on your convention for which direction to make that vector.